All right, we're going to be looking at acids and bases in relation to pH. So on the next slide here, we're going to be talking about the ionization constant for water, that Kw. How do we come up with this ionization constant? Well, we look at water. Let's just say we have a cup of water, and inside that cup of water, we have these water molecules. Um, it looks like nothing's happening with these water molecules, like they're just kind of minding their own business. But if we were to go down to the molecular level, we would see that these water molecules, these two water molecules here, they are actually ionizing with each other. Well, what's happening with that? The hydrogen's positive, the oxygen's negative. There's a strong attraction here. So this hydrogen is going to be pulled off. That water molecule will join the other water molecule and it's going to produce an ion, right? That positive ion, that hydronium ion. And then what's left over, you have OH, which is that hydroxide ion. Let me see if I can get this written correctly here. Okay, so in any body of water, and here I'm just using the cup, this ionization is occurring all the time. It reaches an equivalency, right? There's a point where these hydronium and hydroxide ions are being changed back into water and the water is being changed back into these two ions. The water, of course, is going to be higher in concentration of the water molecules, but they reach a balance, right, an equilibrium. Um, because of that, if we take in a sensor and we drop a sensor into this cup of water that measures the molarity, we'll see that the concentration of these two ions is the same, 1.0 times 10 to the negative 7. Which brings me to the next point that I wanted to make. When you see these ions and they're in brackets, such as they're written here or typed out here, that's talking about a molarity. And molarity in a previous unit we said was the number of moles in a liter of solution. So this is the number of moles of these two ions that are found in a liter of that water. So when we're looking at these two ions, again, they are produced through the ionization of the water, and these two ion concentrations multiplied by one another gives me the ionization constant for water at 25 degrees Celsius. So I can use this equation here to determine the concentration of either the hydronium ion or the hydroxide ion. So in this slide here, they're giving me a substance, right, HCl, and they're asking me to determine the concentration of the hydroxide ion. Well, HCl I know is an acid. How do I know that HCl is an acid? It begins with an H, so that's hydrochloric acid. Next, I'm going to look at how many hydrogen ions I'm going to get whenever it ionizes. And I'm going to get one hydrogen ion because there's only one available from the acid. So I get one hydrogen ion. I use that as a conversion factor over here. So 1 mole of hydrogen ions is what I'm going to get from 1 mole of hydrochloric acid. Do the math and you get 3.0 times 10 to the negative 2 for the concentration of the hydrogen ion. Okay, in online or in your textbook or wherever it is that you look for this information, these two ions are going to be one and the same. So sometimes you'll see them put an H plus, sometimes you'll see them put an H3O plus. Okay, so this concentration here is what I'm going to plug into my equation from the previous slide. 3.0 times 10 to the negative 2 times the hydroxide is equal to 1.0 times 10 to the negative 7. Dividing both sides by 3.0 times 10 to the negative 2, I get a concentration for the hydroxide ion of 3.3 times 10 to the negative 13. The next question asks me if it's an acid or a base. Of course, the answer is already on there, but I'm going to show you how we determine that this solution is an acid. Okay, I'm going to look at the concentrations of the two ions. So here I wrote the concentration in a number that maybe you're more comfortable with or more familiar with. So the concentration of the hydronium ion is 0.030. The concentration of the hydroxide ion is 0.12033. You can see that this concentration of the hydronium ion is much higher and the concentration of the hydroxide ion is much lower. So since this the hydronium ion is what determines the strength of my acid. When its concentration is very high, that means that it's acidic, okay? And the hydroxide concentration is very low, okay? So we're looking at the concentration of this hydronium ion to determine if it's going to be an acid or it's going to be a base. So when this concentration of this ion is much higher, of the hydronium ion is much higher than the hydroxide, it's an acid. In this slide, we're going to be looking at this pH scale, and you'll notice that it's called pH scale. So the values on here are going to be based off of the pH. Okay, if you don't have the pH value, then you can always solve for the concentration of the hydronium ion, and then you can convert that into the pH, and it's going to fall somewhere along here. So I'm going to look at here what it means to be neutral. So a few slides ago, we talked about the hydronium and the hydroxide ions reaching an equivalency. So when both of these are 7, then the pH value is going to be 7. That means that it's neutral. They're both equal to each other. So that's what it means here when we talk about it being neutral. If it runs from 8 to 14, so 8, 9, 10, 11, 12, 13, 14, that means that it's going to be a base. And if it's 6 down to 0, that means that it's going to be an acid. Okay, so what is this scale based off of? Well, it's based off of the concentration of these hydronium ions. So, and it's based off a factor of 10. So if I go from 0 to 1, that means that I increase the concentration by a factor of 10. If I go to 2, that means I increased it by another factor of 10. If I go to 3, that means I increased it by another factor of 10. So they're just increasing by factors of 10. What does that mean? Well, we let's say for example I wanted the number 100, and if I had a base of 10 like I do with the pH scale, that means that I would have to raise 10 to the second power to get 100. So, or in other words, 10 times 10. Well, what if I'm dealing with a very small concentration like 0.01? 0.01, and if I still have the same base of 10, I would raise it to the -2, and that would give me 0.01. So when we're dealing with concentrations of these two ions, we're usually dealing with these kinds of numbers because they're very small numbers, as you saw in the last slide. So that's where this equation comes in here, right? If I want to determine the pH value from this concentration here, I would do a negative log of the concentration to determine the value of the pH that I'm going to put up here on the scale. So let's just say, for example, I use the concentration of 10 to the -2 hydronium ions. Well, bringing down the log and that negative, I would first go to the calculator and I would put log of 10 to the -2. This is 1 times 10 to the -2. So if I do log of 1 times 10 to the -2, I'm going to get a -2. Then I bring down that negative. And so I get a negative times a negative. That's going to give me a +2. So from this concentration of 1 times 10 to the -2, I get a value of 2 on the scale. Let me erase all this stuff up here. So this value would fall somewhere around here, 2, and that would tell me that it is an acid. So that's the way you use this equation here, and I'm going to run a few more examples on a different video, but I'm going to take you into this scale here. I'm not going to really go through this. I'm just going to show you that these are some common household items and where they fall. So if you're interested, you can look at some things that are in your house and see where they fall on this scale. But I'm going to focus more in on this last slide. This is our last slide here. This is the equation that I just showed you an example, a simple example how to use. We can also, if given the concentration of the hydroxide ion, we can find the value of the POH, okay, doing the same process that we did with the previous equation. And then the other equation that I have here is that the pH plus the POH is equal to 14. Again, remember that the values were 7 and 7 whenever they're equal to one another. So 7 plus 7 gives me 14. So, for example, let's say if I had the pH value of 3 and I wanted to know the pOH value, I could just plug 3 into this equation and solve. That would give me a pOH of 11 if they were asking me to do that. If they gave me a pOH of 8, then I could plug it into the equation to solve for the pH. So I would simply take, let me erase this here real quick, if it cooperates with me. So I would subtract 14 minus 8, and that would give me 6. So I would have a pH of 6. Down here, pH of 11. Just, two simple examples using that equation. And then the last two equations that you may need is if they give me a pH and I want to convert that into a concentration, this is the equation you would use. You would take 10 to the negative value of the pH. Or if they gave me a pOH and they wanted me to determine the concentration of the hydroxide ion, then I would take the negative value of the pOH to determine the concentration of the hydroxide ion, just like I did up here with the pH. If they gave me a pH, I could use that value, 10 to the negative of that value to find the concentration of the hydronium ion. Okay, so that's going to be it for this little piece. The next little video I'm going to make is just about solving problems using these equations.